Hi, I'm Alexandra Tsvetkova, PhD student from the University of Toronto, and my project is Java Virtual Machine Footprint Reduction through Java Heap Compression. First, let's discuss the motivation of the project. Java applications are very popular because the same application can run on any device or in the cloud. As you can see from the slide, in the cloud, memory is the most expensive part of instance price. If Java applications use less memory, it could help to reduce cloud costs. The application would be able to run on a server with less memory, or we could fit more applications on the same server. One of the ways to reduce the footprint is to reduce the amount of memory required by Java Heap. Previous research showed that application heap can be reduced up to 86% with 58% average by using compression. In the GenCon garbage collection policy, OpenJ9 uses weak generational hypothesis to divide objects in two categories, short-living objects and long-living objects. Some objects become unused very fast, but the ones that don't usually stay in memory for a very long time. It's counterproductive to compress objects with a short lifetime because of the compression-decompression overhead. Hence, in this project, we will focus only on old objects resided in tenure area. We estimated tenure area compressibility potential to be 3x to 5x, which aligns with the previous research findings. We also noticed that the tenure area has some empty space, especially when the program starts. It's one of the reasons why the heap compressibility changes over time. This picture shows us the object lifecycle. We have two areas, nursery area for young and mostly short-living objects, and tenure area for old objects. Initially, objects are created in the nursery area. When the allocation space is full, local garbage collection happens. It moves long-living objects to the tenure area and shorter-living objects remain in the nursery, but in the survivor space. As we discussed before, it only makes sense to compress long-living objects. The compression part is done at garbage collection time. You can see it in the picture. Decompression is done on every memory access, whether it's a read or a write. Decompression is done on critical path, and it's important to make it extremely fast. Right now, we are using bytecode injections to perform decompression. In this project, we are going to use page-based compression. That means that we are going to compress whole pages rather than separate objects. Let me guide you through my compression protocol. We use multiple tables to store additional data. In order to determine whether the current page is compressed or not, we will need a metadata table. For every page in tenured area, we have one bit in the metadata table saying whether the page is compressed or not. This allows fast checks for uncompressed pages, with the access time big O of 1. If the page address is modified, we need to look in another table that's called address table in order to find the new address. This table contains all the new page addresses. Write protection table ensures the safety of concurrent memory accesses. When a write is happening, the write protection table is raised, and that is atomic. This will ensure that two concurrent writes can't happen at the same time. One of the problems that we are trying to address is using bytecode injection for all Java classes. We're injecting a function for every memory access in every Java class. But some of the classes can't be modified easily because they are loaded on the early stages of Java Virtual Machine launch, so no additional classes are available for injection in system classes. In order to overcome this difficulty, we had to add an extra check in our bytecode. The decompression function is not called if the first garbage collection hasn't happened yet. Let me summarize our progress so far. First, we evaluated compression potential and realized that tenor compressibility varies between 3x to 5x on average for the applications in our pool. Second, we created a protocol that will allow concurrent memory accesses when memory compression is done. Third, we implemented compression inside of the OpenJ9 garbage collector. Now let's talk about the next steps for the project. We still need to finish the decompression part and evaluate performance overhead for our solution. After my system is fully functional, we can try different performance optimization techniques, including both compression decompression overhead reduction and reducing injection cost. We can separate hot and cold objects inside of the tenure area and compress only cold objects. We can pick the best algorithm to ensure good compressibility performance trade-off. Eventually, we will move decompression into code generator. Overall, I think that the project has a potential for memory footprint reduction 3x to 5x, but still more work is needed to optimize the performance of our design.